There are more sophisticated methods to derive the equation for the pressure of an ideal gas. But if you're looking for an easily understandable and straightforward derivation of the gas pressure equation using molecular kinetic theory, here it goes. Trapping a volume of gas inside of the container, the pressure inside is caused by individual particles colliding with the walls of the container. Let's zoom in on one single particle and isolate it from the rest of the gas. This particle collides into the wall with a momentum mu, where m is the mass of the particle and u is the velocity. Making the assumption that this collision is perfectly elastic, the particle will rebound with a momentum minus mu. They are the same magnitude, but the negative sign tells us that the particle is now traveling in the opposite direction. So the particle's change in momentum is the final momentum minus the initial momentum, giving us minus 2mu. Do you remember the impulse equation relating the change in momentum and force? Force is equal to the change in momentum divided by the time of impact. Substituting this into the impulse equation, the force that the particle exerts on the wall is minus 2mu over their contact time. But we are more interested in the force that the wall exerts on the particle. So according to Newton's third law, the wall exerts an equal but opposite force on the particle, which is just 2mu over t, allowing us to drop the minus sign. I'm going to redraw this diagram so that we can see all the sides of the container with the 3 dimensions x, y, z. We're now going to utilize the most basic equation, speed is distance over time. The time it takes for this particle to make it from this side of the container to this end, and then back, is 2x over the speed of the particle. Plug this back into the impulse equation. We get the force exerted by one particle to be this. But by definition, pressure is force over area. The cross-sectional area of this container is y times z. But the volume of this whole container of gas is equal to xyz. The equation for pressure now reduces to the mass times by the speed squared divided by volume. This is beginning to look a lot like the kinetic theory equation that we're trying to derive. But where has the factor of a third come from? Well, pressure is a scalar quantity that acts in all directions. The increase in pressure caused by each collision will on average be distributed evenly in each of the x, y, and z axes. So we need to divide the right-hand side of the equation by 3 to take this into account. But this is pressure due to just one single molecule of gas. If we have n number of molecules in the gas, we have to multiply by n. We're almost there now. All that's left is the subscript RMS, which stands for root mean square. To find the root mean square of a set of data, we need to square each number, add them up, divide by the number of data points there are, and finally take the square roots of everything. This is a mathematical method used to find the average speed of the molecules in a gas. Since there are n number of molecules in our volume of gas, to find the root mean square speed, we have to square the different speeds of the individual molecules, add them together, and divide by n before square rooting everything. So here we have the final form of the equation for gas pressure derived using the concepts of molecular kinetic theory. Thanks for watching this video on molecular kinetic theory. Be sure to subscribe for more physics.